So who is PROTOS? We develop software tools, test tools, and software architectures for embedded systems. So today we're talking about software tools, test tools, sorry, for embedded systems. Who am I? I'm an aerospace engineer who likes embedded software architecture, tests, and tool chains. And I'm the founder and CEO of PROTOS. Okay, let's dig into the meat. So why are we here today? What do we want to achieve? What's the problem? Late testing of an embedded system is a real problem, and it's extremely expensive. So what we really want is we want to bring the tests as near to the implementation as possible. So the unit tests, yeah, they can be run during the implementation, but integration in systems tests usually not. We need fast feedback. We need to learn and test earlier. That's very important to speed up the project and to save costs. So let's have a look at the development cycle or a development process. Usually you start to develop your embedded software on an evaluation board. On the right microcontroller, you program or configure drivers. You program hardware-related software components, such as a motor controller or a battery controller or bus protocols. And on top, you have a lot of software components for your application. You integrate everything to your complete application. And at a certain point in time, you go to the real ECU, to your real hardware. And yeah, and then the question here is, when do you test? Normally, most systems are tested in the early phases only for the software components with unit tests. This can be done, for example, with Tessy. Many of you probably are familiar with the Tessy toolchain. And later in the process, usually you have a HIL test system or a real test. Run a real test, so you sit in the car and you drive around the block. This would be a system test. If you simulate this, then it's a HIL system test. And additionally, we provide with a miniHIL solution where you can run a hardware-software integration test early in the process, continuously, and so on. And by that, we bridge this gap here in the tests, especially for the software development. So most embedded projects are not really good tested in the early phases, and that's what we're talking about today. So what do you really want and need in order to test fast, early, and so on? You want to test what is changed most frequently, and that's your software. So the hardware is not changed that often, but the software, for example, could be changed 10, 20, 100, 1,000 times a day. I don't know, depending on, of course, on your team size and on the activity in your project. But it's typical to have 10, 20, 30, 40 software changes a day. So you want to test this very frequently. Then you want to test every code change of every developer within minutes instead of weeks. You want a full regression test also for unrelated code. I'm sure you know the situation. You change something in the upper left corner, and in the lower right corner, an error occurs. You haven't changed anything there, but you have side effects in embedded software. You have a pointer, you have a null pointer, or whatever, and or you have shared resources, and this can lead to all kinds of regression problems here. So you want a full regression test for everything. Then you want the full test automation to enforce tests. So you should not depend on every developer to run the tests. First of all, it costs a lot of time for the developer, and second, you're not sure whether the tests actually ran or not. So you want a test automation, and in the end, you also want a automated hardware in the loop test to test more than pure software units, because the software units are in an embedded system only a part. So why is it so hard to automate tests for embedded systems? Let's have a look at the example of a motor control system for an oil pump. It's a safety critical system, and they needed to test so it's a real world system, real project. They needed to test all border values for 300 relevant system states. Let's have a look at the system setup or the test setup before. They had a climate chamber with the complete system, so with the complete ECU, with the power electronics, with the motor, with the pump, hydraulic system, and so on. It was scripted, but the script never ran automatically, and the test would have taken something like 30 days for all the states. This was never done, so at least not complete. So what we did is we pulled out the microcontroller of the system with the complete software stack, and we simulated everything else with our miniHIL simulation. We got it down to 50 minutes, completely automated. So it's easy to automate if you work with simulation. It's not so easy to automate, or sometimes impossible if you bring in the complete system, if you test the complete system. And it's also really hard to test the failures. With a simulation, you always can have failure injection by manipulating the simulation and so on. So let's have a look at the same system from a perspective of test levels. So let's start with the smallest test level. This would be a unit test. Unit test typically tests a single C module or a class, something like that. And so that's a unit test. You can use Tessy, for example, for that. And the next step would be a software integration test, where you integrate several software units together, maybe a lot of software units together. This can also be done usually very good with a tool like Tessy, with a unit test tool. Then the next level would be hardware software integration test. You take the microcontroller and you test the microcontroller with its software as a black box by stimulating all the pins, so all the signals at the pins of the microcontroller. And that's basically the smallest possible hardware in the loop test. So this can be done with a miniHIL, and all those tests run really fast. Then the next step would be a hardware in the loop test. So with power electronics, with the sensors, with the actuators in the loop. Yeah, sometimes you don't take this power electronics in the loop, sometimes you do. So there are also various levels you can run hardware in the loop on. And in the end, you need a system test. The system test is very important to really validate what your system actually does, the top level requirements and so on, so that the system does really the right things. Basically, you need all those levels, or you can use all those levels. Maybe you do not use all those levels, depending on what kind of system you have. Maybe it doesn't make sense to use all those levels, or it's too costly. But in the end, let's have a look at the effort and the speed. The unit test is the fastest and most inexpensive test you can run. You can run it whenever you change something. You can run it very often. Software integration test, almost the same. Hardware software integration test is already a bit more expensive, but it's still very fast, and you can run it often, but it's not so inexpensive anymore. Then a big hardware in the loop test is much more expensive and usually is not run that often. And a system test is in many cases manual or partially manual, so you will not run it very often, but it's very, very important. So it's not about the importance, it's about the speed and the frequency and the price here. But in the end, if you run a system test, you do not want to find software errors, because it's just too expensive to retest in a system environment a software error. You want to find the software errors or the integration errors much earlier, at the earliest possible point in time. Let's have a look at the response time of the different test levels. Let's start with the unit tests. First of all, the most important thing I'm talking about here is speed. Speed is the message. So we want fast tests on every change. So we have two levels where we can do this really, really good. That's the component and the integration test level. Usually integration tests are not done very often, at least hardware-software integration tests are not done very often. And the system test already is usually very slow and expensive. So it's run every other week or every other month or something like that. Acceptance tests usually are system test level, so they also don't run very often. So let's have a look at the lower two levels. On the lowest level here, on the unit test level, and on the software integration test level, you can use a unit test framework like Tessy. And the next step, you can use the miniHIL for hardware-software integration tests. Both test levels can be executed within minutes. So on every commit, for example. So that's the focus now of the demo I'm going to make. Let's have a look at a brief look at Tessy for unit and software integration tests. It's a very nice framework with a structured model-based definition of test cases with classification tree editor. I personally think that's a very nice solution to really have a structured approach to design your test cases, your border values or boundary values, your equivalency classes, and so on. And it also comes with a code coverage, not only for the execution on the host, so on a server or on your laptop, but also on the target. That's a very nice feature. You can use very good for certain qualification topics. And of course, there are many, many more features to this unit test framework. So that's what I'm going to use for the unit tests of the system. Then the next level is the hardware-software integration test. Here we have our miniHIL system. It's very small. And the goal is to test the microcontroller with the complete application software and all the drivers and so on by connecting the pins of the microcontroller to the test system. So those are the connections here. We connect, for example, PWM with a wire jumper here with the test system. And you have all the low-level IOs like digital, analog, SPI, low-level bus systems, PWM, and so on. And on this side, you run usually the environment simulation, for example, for a motor, for a battery. You have a plant simulation running, and all the test cases you need to verify that your system actually works in this integration with the microcontroller. So it's really the right microcontroller and with the complete software that as it is in your application, in your system. So the development process, we need to develop the environment simulations and the test cases. Is a model-based process. So for the miniHIL, we developed the simulation and the test models. Then we generate the code in C. We compile this, we flash this to the execution target here. So basically to this processor. Why do we do this? Why don't we run it on a PC? Because we need hard real time. For a motor control, you need 20-30 kilohertz, for example, to simulate this. Or you want to know whether error shutdown has occurred in the right time in 100 microseconds or 10 microseconds or something like that. And for that, you really need hard real time. This cannot run on a PC, for example. So then next step is we log the reports and we transform them into diagrams in order to understand much better what happened in your system. To have an overview like a feature or requirement coverage report, or also those low-level diagrams like a sequence diagrams that points you exact to the place where your test case actually failed and why. And then you learn and iterate. So that's a very short cycle here. So next step is continuous integration. So we talked about the test levels. Now we want this automation I've been talking before. So why do we want continuous integration and how does it work? We want it for automation. So we want to enforce the tests, whatever is changed. It doesn't matter whoever changes the system. Let's have a look at the integration problem to explain why continuous integration is such a good idea. Let's imagine you have an integrator. This can be a person, or this can be a team. This can be a role in your company. So somebody has to integrate all the software and hardware components and so on that are developed. So the first developer commits 20 changes. We're talking about software changes, of course. And then next one, 50 changes, 30 changes. And suddenly we have a couple of hundred changes by developer 4. The integrator is not really happy about that. And some more changes. And in the end, the integrator cannot handle this anymore. And this is integration hell. That's really the saying for this situation. And the problem is that all those changes are usually committed or integrated minutes or hours or maybe a week before the release. Sometimes even after the release, you know the situation. And suddenly you have all those changes, and of course there are effects, there are combinatorial effects, there are things that are not compatible anymore, and all those kinds of problems. And that's integration hell. So the idea is now to make those integrations whenever something is changed, so continuously. And that's what the continuous integration server is for. So every developer changes something, commits it to the source code management. The source code management triggers the change in, for example, in Git, triggers the continuous integration server. In this case, a Jenkins can be any kind of continuous integration server that suits your requirements. And the server checks out the last change, automates the build, automates the test, and automates the release. Please always automate the release. That's a very valuable thing to automate. And in the end, you want a very, very fast response. So it's also important that every change is integrated and tested. So from my perspective, there's no reason not to trigger the build process and the test process with every commit within seconds. Early and often is the motto here. So you also need to commit early and often to fail fast. Because if you fail fast, you can detect the bugs very early in the process, and you can fix them sometimes within minutes. So very early in the process, you don't have any conflicts with other developers, and you still know what you changed. So you want to know this within minutes, or let's say at least within an hour or so. You should get a response by the continuous integration server, and you get an email because you checked it in. So you get the email, and you can fix this immediately before even somebody else commits his change. So that's the basic idea. The problem is, in order to automate the tests, we need automatable tests, which is easy to do in software, not so easy to do with hardware in the loop. Let's have a look at the setup for continuous integration with the miniHIL. We have a special situation because we have a hardware in the loop. So every code change goes to the continuous integration, as we've seen before. The software and the test system is built automated, is executed automated, and is delivered. And here you see a setup for 8 miniHIL projects. So 8 different projects, here with an Oryx board, here with an STM32, and so on. So 8 different projects in a rack attached to the server. The server can use this hardware to really run its hardware in the loop tests, its hardware software integration tests. So that's a typical setup for continuous integration with hardware in the loop. Every code change of every developer for every project can test it within minutes. If it runs longer, then make 2 stages, one commit stage that runs short and another stage that runs longer. So you want fast feedback. Now let's have a look at my continuous integration setup for my demo. On my laptop, I have the development environment for both tools, for Tessy and for the miniHIL. And I have attached to my laptop, I have attached a miniHIL board. I can show you that. So that's really my miniHIL board here. So it's exactly the setup as you can see it here. With the laptop, I developed the Tessy unit tests and the software integration tests. And I developed the miniHIL environment simulations and the test cases for the hardware in the loop system. Then we commit this to a Git source code management. It runs locally on my laptop because then it's for demo purposes. It's much more stable. I do not rely on an internet connection. And the same is holds for the Jenkins server. I have locally also Jenkins server, but usually this also runs on a server. So this Jenkins server is triggered by every commit in the source code management system. Then first it builds flashes and runs the test on the miniHIL and reports the results again to this Jenkins server. And the same for the Tessy tests, but the Tessy tests are not run, of course, on the miniHIL, but they're run locally on the server itself, or sometimes also on a target as processor in the loop test. That's also possible. And yeah, so now we have the both reports, and then we can have a look at what failed. And so that's how we develop the tests. But of course, much more frequently, we will develop the system under test. That's in the end why we want such a test. And every change in the system under test, in the C code, in the MATLAB models, whatever it is committed, and every commit triggers exactly the same process on the Jenkins server. So it doesn't matter whether you change a test case or you change the system under test, it's always the same process. Very important here. Okay, let's have a look at the demo system test setup for the hardware in the loop, for the software in the loop. I explained to you already the unit tests here. Hardware in the loop is a bit more complicated, of course. So we have in the system under test, that's here on the right side, this microcontroller. We have an STM32 Cortex M4. It runs a motor control application. That's a typical application of many projects with a BLDC motor. So the motor controller generates 3 PWMs. In the test system, the processor, the test system measures the PWMs, and on every change on every PWM phase, it generates a new speed. It calculates the new speed as an environment model for the motor. And according to the speed, we generate Hall signals as digital outputs. So the motor controller can really control the simulated motor instead of the real motor. And then we have a temperature sensor. We simulate this by providing an analog output. And on the other side, on my microcontroller, I have an analog input. And then we control the speed and the direction and so on with a UART, so with a low-level bus system. And in the end, now we have a complete simulated environment. And based on the simulated environment, I can bring my system under test into any state I want it to be. I can destroy signals. I can make failure injection by doing the wrong temperature or whatever I want. Since it's all simulated, except for the signals, the hardware signals, everything else is simulated, so I can do whatever I want with the system. And that enables a lot of different test cases. Good, that's the electrical level for those test cases on the miniHIL board. And for example, you can change the speed, you can stop the motor, you can verify whether the motor really stops on a low or high temperature. On a warning temperature, we can check the limp home functionality, and so on and so on. So those are typical test cases you can run in the hardware software integration test. And the integration point here would be so to the rest of the system, the pins of the microcontroller. That's the border where we actually test. That's the black box. So let's start with the live demo. Locally, I have installed the Jenkins server, Git repository, Tessy as a test environment, and the miniHIL environment. So let's jump right into the meat here. That's the miniHIL development environment. So if you have a look at the system under test, that's the system under test, and that's a test system. So everything I'm showing you now is the development of the software on the test system, so the environment simulation and the test cases. So everything that's in this box, it's a so-called actor, will be generated, compiled, and will run on the miniHIL test processor. So I double click, I go inside this demo. Here you see the I/O layer with the digital analog adapters, UART, PWM duty capture unit, and the Holt generator for the digital outputs to simulate the motor. We measure the PWMs. The measurement goes into the motor simulator. The motor simulator calculates the new speed and propagates over this port of the whole gen out port the speed to the whole generator, and it simulates the whole sensors by using digital outputs. So that's the I/O landscape here. So now the simulator needs a bit of behavior. This can be a generated Simulink plant simulation, for example, in C. But this can also be a state machine. The state machine can be modeled inside this method here. I open the behavioral editor. That's a state machine. So if the PWM comes in, the new duty cycle, then we memorize it as a member variable. Then we go into calculation. We calculate the speed, and then we set the new whole, for the whole generated, a new speed. So everything I can do here is available from the model. I can change the speed, I can change the direction. I could, for example, change the direction or set the wrong speed to see what my system under test does. So that's failure injection, and to see what happens, whether my system under test detects the error and, for example, generates the right error message. So that's the simulation environment. Here I have a little motor temperature simulator. The test case can set the temperature in degrees Celsius, and this block here transforms this into an analog output. For example, for C, set 10 degrees centigrade, maybe it's 1.1 volt at the analog output to simulate the environment. Okay, so the test case here has access to the temperature sensor simulator, to the UART, for example, to change the speed of the motor, and it has direct access to the motor simulator, for example, to manipulate the motor simulator to destroy a signal, or to measure whether the motor actually controls the right speed. Okay, so the last thing we're missing here is the test case. The test case is also a behavior in the model. So that's a test case in this language here. And you can define steps and sequences. And by doing that, you can exactly define what happens. For example, here, activate motor control. We set the direction. We activate the brake, for example, of the motor, and so on. And here you have the textual specification. You can change this here. And on this side, you see the graphical specification. That's just a view. That's good for people, for persons to really discuss the behavior of the test cases. And on top, we have the test suite that really defines the complete behavior of the test case here. Okay, so that's how we define the test cases. And now let's have a look at the system under test. So system under test is here. And now I'm going to modify the system under test. I'm going to change as a developer of the application. I'm going to change the behavior. And let's two different things. First of all, I will change a very fine-grained, make a very fine-grained change to the temperature limits here. So I changed the temperature limit by 0.1 degrees, and that's something you cannot really find from an integration test perspective or from a system test perspective. So that's something that's very fine-grained, very low level, and that's something you can find really good with a unit test. So let's change this. It goes to the Git repository. I add the change to the Git repository. I make a commit, say bug 1, and I commit this. And let's go to the continuous integration server and see what happens here. And you see it immediately triggers the test cases here, or the continuous integration process. First, we run the Tessy test, so the unit test, because that's the low-level test. We could run them in parallel, but for this demonstration, it's better to run them one after the other. Here you see also the motor control miniHIL, the integration test has been triggered, but first we run the Tessy test. So the Tessy test is already executed. It already checked out the new software version, so this line of code that I changed, and it's running the tests here. Let's have a look at what happens inside. So basically, we're running all the unit tests for all the units here, and they can really access everything in the module. Yeah, unit test is a black box test, but it has white box information. So in this case, it will find the very fine-grained things here. Okay, so let's have a look at the Tessy run. It's still running here. Does a lot of unit tests, and in the end, we expect that the Tessy test detects this problem, and that the miniHIL integration test, since it's not so exact like the unit test here, will not find this problem. That's what we expect. So, okay, so the Tessy test failed. Let's have a look at the dashboard. The miniHIL test is running now. So while the miniHIL test is running, we have a look at what Tessy does here. So latest test results. Yeah, we see the check temperature fails. That's exactly what we expect. So the temperature is either too high or too low. And in the miniHIL test, meanwhile should be done. Let's have a look at the miniHIL. It also checked out and assembled the test, flashed the test and the system under test and the test system, and now runs the test on the miniHIL board, and everything is green. That means the miniHIL test did not detect this error. It was too fine-grained, so it's really hard to stimulate everything from the outside as a black box at the pins of the chip. But if I make a different change, something, for example, in the timing of the processor, or in the operating system, or in this case, I'm going to fix this problem here, and I introduce another problem. I change the resolution of the ADC. Then we will see what happens now. So I fixed the one problem and I introduced another one. So let's call this bug 2. And let's again have a look at the situation. So here in the dashboard, we see currently the motor control test with Tessy failed and the miniHIL was okay. And now again, the Tessy test has been triggered. It's running now, and the motor control with the miniHIL test is running after that. Let's again have a look at the at this picture. So now the unit test is testing again all those units and also the software integration here, and the miniHIL is testing this here. So I modified something in the drivers, or I have a side effect by changing, let's say, compatibility between the software element and the driver and things like that. And that's something the miniHIL can find very good, and it's really hard to find something like this with a unit test. So let's go back to the Tessy test here. It's still running. So should be done any minute or any second, hopefully. So before it has been yellow, now I expect this test to be green. Yeah, it's really live demo, so of course this takes a while. We have a couple of tests in here. So now the Tessy test is green. Now let's go back to the miniHIL test. Now the miniHIL test is running. It's currently flashing the board. Here you see the LEDs have gone. Now they're on again. So this miniHIL board has been flashed. Now the system on the test has been flashed with the new code, because that's what actually changed. And now the tests are running. Have a look at it. So here we see the tests are running. That's the command line log. In a couple of seconds, this should be finished. And then we can have a look at what happened. So now we see the miniHIL test is yellow. So here, dashboard, you see now it's exactly the other way around. The miniHIL test discovered this problem, not the unit test. And let's have a look at the trace, integration trace. That's again the same trace or the same format we had for the specification, but now that's the logging. We convert this logging into the sequence diagrams, and here we see actually the motor control speed test failed. That's a surprise. And the test limit temperature failed. That's not a surprise because I changed the temperature. And again, here's some other test break test failed. So that's interesting because the integration test detected more errors than expected. In this case, for example, the normal motor control doesn't work anymore correctly because it always runs into a temperature problem. So that's a typical effect of the detecting side effects with such a test. So when I click on the expect failed here now and go back to the IDE, I see in the IDE, I see exactly the position where the test case failed. Okay, so that's it from the live demo side, and let's go back to the slides. Yeah, that was it from my side. If you have any questions, please contact us. Michael Weiss for the Tessy tooling and for the Hitex part, and from my part for the miniHIL and the integration tests. Feel free to contact us. We're happy to discuss with you your use cases. Yeah, thanks for the attention.